So isn't it?
The averages are going up, so you should be this spring should be pretty mental, actually.
Okay, we're gonna start recording here. You can still chat amongst yourself because I just cut this off the front end when I edit it. But just be careful about certain words.
Or singing songs.
Okay.
Nothing out there yet, huh?
Okay, and
Well, that's
folks, mute stuff when you get a chance. Mute your own or co-host, help mute them.
Sometimes I like to hear them.
You want to hear that?
Yeah, and if they get boring, I'll ask you to put your headset on.
Okay. Fun. Everybody ready? Oh, now I'm going to get the giggles. Good morning, Cycle 25. We have a special guest today. The guy that kind of started the name of this channel, all things considered, Dr. Scott McIntosh is here to provide us with an update on what's going on with Cycle 25. I like to brag that we were believers in Scott before other people were, way back when. I guess our last update was like 16 months, 18 months, Scott?
Something like that.
Yeah, absolutely thrilled to have you back. Glad that you're able to get some time with us. I know you're doing a lot of press stuff and a lot of good information is being had out there. There is also, and I think we'll make reference to it at some point in the presentation, there is a paper that Scott has just released. About a week ago or so?
End of January, yeah.
Yeah, so I do suggest that we all go back. If you haven't read that already in the links that I sent out prior, please go back and have a look at that because it is really cool. So with that, Scott, I'm going to say that go up and share your screen. We'll get everything tidied up and then we'll start this thing going because we are live on YouTube.
All right, okay, thank you. Thank you, Rod. Let's see if I can go into play mode here. Everybody seen that okay?
Yes, perfect.
Yeah, there's a bit of shameless imagery here, right? A visual that's provided by my friend Tamitha Scott, who some of you may know or be familiar with, or more commonly known as the Space Weather Woman. So she's just a mega star, really good friend of mine. We've known each other a long time. And she was actually the one that encouraged me to reach out to this community. And now I'm paying for it, right? So
definitely.
Anyway, hat tip to you all. Wearing some shameless propaganda as well. So good for you guys. And I'll get going because the kind of rough title of this one is Sunspot Cycle 25 update after the Terminator, right? So the last time we spoke, we were waiting on the Terminator. We were waiting on Arnold showing up in his Harley to flip the switch on the sun so that Cycle 25 could really get crack-a-lacking. So we'll get there. Hold on. As I warned you, I am now being engulfed by my children. So they will be zapped with the taser and sent to another part of the room. So anyway, so I'll leave that up there. That, of course, is a kind of nice segue for where we were when we last spoke. Yeah, I believe it was September 2020, or maybe it was June 2020. I can't remember. But we were wildly speculating about what Cycle 25 was going to look like, in great trepidation about whether or not the putting the proverbial things on the slate was a good idea or not, and where the tea leaves were kind of headed. So that's the kind of contextual image. We'll come back to this plot later on as I update it because almost 2 years have passed. Not quite, but close enough. In astronomical terms, it's about 5 years. But anyway, so you have our forecast in red stacking up against the mean of the sunspot in green. So that's the historical mean, or as I often call it, the hysterical mean. And then we have the blue, which is the kind of community consensus forecast that was put together in 2019, right about the same time that we were coming up with the red curve. But one of the interesting things about the red curve is that we always offered ourselves the opportunity to revise, because the event that we were waiting on hadn't actually occurred yet back in the last time I spoke to you. So it has. It did exactly what it says on the tin. So for those of you in Commonwealth countries that are familiar with Thompson's water seal and the commercials about that, and there may not be any, but yeah, it does what it says on the tin, right? So anyway, here's another snippet of where we were. So it was clearly in June of 2021. Okay, so we hadn't got there yet, but we saw that there was a quite possible that the sun's behavior was starting to follow the track, between the red and the green tracks, right? Somewhere between the historical average and our very speculative solar cycle amplitude that got everyone kind of excited. So even since the last time we spoke, in fact, in the last week, the sun's been doing this stuff. So, like the graphic behind my head, we've been observing the polar vortex, or whether the sun actually has a polar vortex or not. It has a very regular and very interesting polar evolution. And if I get to that at the end, I'll put this craziness in a little bit of context for you, and why I'm so bloody interested in this, right? Yeah, it's rare. At least it's rare because I've never seen it before. And not to say it hasn't happened before, but anyway, we'll get back there later on, but there's certainly nothing to be worried about. All it does is it illustrates that there's some really cool shit happening on the sun at high latitudes. That's all it really does. But it is a critical piece of how the sun's dynamo works. So, and the fact that it's shedding material is fully anticipated, right? Because what happens is magnetic fields get stressed as they're constantly churning and playing kerplunk with themselves. Stuff gets ejected off, and so it's actually a good sign. This means that the progression towards solar maximum is fully kicked in, and we're I'll get there later. For those of you that didn't read the paper, I'll get to that point and an update on those plots. So, a quick recap. You may remember this movie. This is an evolution over several decades of what the sun's magnetic fields look like. And of course, this is the $64 billion question is, can you understand this thing, interpret it, and then forecast how it's going to play out? One of the things we've learned over the last decade is that this is really just the tip of the iceberg, literally. So these magnetic fields that poke through the sun's surface in a kind of, in a bubble. So you see one polarity going one way in blue and the other one in red or yellow. Sorry, I flip colors all the time. Indicate that the field's going in and out of the sun, basically. And you see its evolution over several decades. It's pretty much a buoyant process, so at least we believe it's a buoyant process. There's a lot of physics that's consistent with something being more buoyant than its surroundings, and it rises through the atmosphere. So, what have we been tracking since 2002? And in fact, 2002 rigorously are these small objects in the sun's corona. So in the image on the left is the 1.5 million degree corona. It's an emission line of iron 12, so 11 times ionized iron. Let's not get into spectroscopic nomenclature, but it's basically hot shit, okay? And one of the conundrums about the sun's outer atmosphere is, as many of you know, right, there's this coronal heating mystery that the surface of the sun's at about 6,000 Kelvin, but there's this cloud of very hot material sitting over the top of it, which is at millions of Kelvin. Yeah, it's not meant to work that way, at least not in a kind of regular thermodynamic world. It's like opening your fridge and your kitchen gets warmer, right? Just think about that one for 10 seconds while your brain melts. So that's one of the great conundrums. You'll see that object is percolated by these little spots. So they're small. They're of the order of, a few tens of thousands of kilometers across. Okay? And in the sun's context, that's pretty small, right? But each one of these things is about the size of our planet. So on the left is the undetected thing, and on the right is where I apply my very special algorithm to it, and it identifies all these dots. Believe it or not, it's actually fairly straightforward analysis. My old supervisor at the time, what did Joe know? Joe Gurman, I always credit Joe with this, is, you should identify and track those little things in the corona. You never know what you're going to find. Paraphrasing. There may have been expletives in there, there may have not. I'm not going to attribute those to Joe, but I think Joe pretty much knew what we were going to find if we looked for long enough. So this is an excerpt from an email I sent to a friend in 2012. Okay, a colleague, Maura Hagen, who's a pretty famous person now in a national academician. Is that the right word? I don't know. Anyway, she's on the National Academy of Science, and she was my boss's boss's boss in 2012. And I'd known Maura a long time, and she was interested in what we were doing as a lab and what new science was coming out. So I said I'd had a kind of eureka moment, and I'd noticed something weird, right? That I'm tracking these features in the sun, and I can see very strong overlaps in the pattern, especially if you look at the one in the bottom. And all of a sudden, the pattern stops at the equator, and then I get massive growth at mid-latitudes, and this is really bizarre. So two things: the sunspot cycle doesn't overlap this way. So that's the horrible plot in the middle that you can't see very well, because it's 2012 and we were all into rainbow colors then. Oh, wait a minute. Okay. Anyway, and then in the bottom figure, you can get an idea that there's a multi-year overlap in this pattern, right? It's not a few months, it's extended. And of course, this is a snippet of a greater thing. And we actually noticed that this thing went up to much higher latitudes than sunspots, which typically form at about 30 degrees latitude and then move towards the equator, okay? Annotating the crap out of this thing, so this was, believe it or not, was the next slide, which is a complete stream of consciousness thing, kind of thing, and I'm just giving it to you, okay? Was that, look at all those little boxes. Oh my God, solar minimum. There's 4 bands present at solar minimum. I thought there was nothing on the sun at solar minimum. Holy crap. But there's 4 of them. And then in the ascending phase of cycles, there's only 2. Holy crap, what's that? So this is kind of me expressing my artistic frustration with what I'd found, right? So if you want to spend a second reading those, what you're basically seeing, it's the genesis, the progenitor of a concept, right? And I'm like, wow, this whole idea that the sun's making no spots, yet there's 4 of these bands present, was kind of amazing to me. But then the kind of eureka moment was identifying this event that happens in time, where all of a sudden something dies at the sun's equator, and just by magic, shit switches on at mid-latitudes. If you read the solar physics textbooks, and I don't recommend it, right? Actually, I do. There's actually some really good stuff in there. But what they'll tell you is, because of the kind of what we call the a priori assumptions that you make when you do the calculations, so the assumptions that go into the physics to simplify the math, right? Well, they make an assumption that the bands in the inside of the sun, where the sunspots form, don't talk to one another, right? So in other words, they're locally disconnected, or they're globally disconnected from one another. That's a kind of very coarse way of saying it. Well, all of those bands have opposite polarities. I'll get to that in a little minute. And for those of you that have dicked around with magnetic fields, you know that opposite polarities want to attract and cancel one another. That's one of the beautiful things of magnetic fields, of course, if you mess around with Maxwell's equations, the whole point is everything balances and cancels. So what if this whole thing is about balance of magnetic fields, and it's not about and connectivity of magnetic fields, and it's not about just the internal large-scale flows inside the sun? What if? Okay. Well, what if I can play forward in time? And so on my sample of, 14 years, 16 years at this point, I said, things look very linear. Let's have my 5-year-old draw some straight lines. Okay. Super linear. And also, I'd done a little bit of detective work looking back in the past, and I'd identified that the polar cells, up at 55 degrees latitude, everything was actually very robust. So every 21.8 years, it seems like it repeats a cycle. It's like, that's weird. Haven't seen that in the literature anywhere. Anyway, so dig a wee bit deeper. I go, 5-year-old. Yes, Dad. Come draw me lines. They start here and they look at kind of like that. So the pink lines, do you see those pink lines, the magenta lines on here? Do you see the red lines? So the red lines were the continuation of cycle 24 towards its impending doom at the equator, right? Based on a straight line drawn by a 5-year-old. Okay. Not a PhD, I will add. The magenta lines were the forecast for cycle 25. Based on this cyclic behavior that every 21.8 years, shit happens. Okay. Whether you know how it happens or not, it happens. Should I flip-flop back and forth? How's that? Hey, that's pretty damn good, right? So by this point, we're trying to publish a paper that, hey, we've actually seen cycle 25 now. It took a year and a half, right? Furthermore, cycle 25 is exactly where we expected it to be in 2012. And that paper took a year and a half to publish, right? So where are we at? Okay. Time to think a wee bit harder. Okay. So the data's following a kind of pattern, at least. And what was lobbed at us at the time is we're cherry picking, right? We're cherry picking. We're only picking the data that replicates this model. Good luck. All right. So here we go. So now you start to look and you start to see some other cool phenomena, right? So here's the sunspot number as a function of hemisphere and latitude, right? So red and blue are north and south, black is total, and then there's the sunspot distribution on the bottom. Just for shits and giggles, I drew 2 of these termination events where things end at the equator. Yeah, there's kind of rampant growth in sunspots at those points. There's all kinds of things going on. The number of sunspots also does an amazing thing, which is also not in the literature until we published it in 2016. Do you see those very large excursions in the sunspot number in the hemispheres? Right? It's not just a linear kind of, they go wham, 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 wham. Like the order, almost an order of magnitude oscillation over the timescale of about 11 months. That's still fluke. Won't get into what that is, but it's pretty cool because that's what ties understanding the Earth's weather to understanding the sun's weather. So anyway, so standing on the shoulders of giants who'd done some of this work before that we discovered when we were 95% of the way through publishing our paper, they called this thing the extended solar cycle. We've got a step further and identified that it's one and the same with the sun's 22-year magnetic or pale cycle. So you'll be a bit more familiar with this schematic from our last conversation. So now I've colorized the magnetic fields in red and blue, positive and negative, and you now see categorically that when the sun makes no spots, there are 4 oppositely signed bands around the equator. Maybe they cancel to make no spots. And if it's a buoyancy thing, it's all about pressure. So the basic idea here is it's about the amount of available free magnetic field you have, because that creates a more buoyant environment for the magnetic feature to rise. So if everything's locked down, right, I don't have any free magnetic field and things can't rise. But if I sever some of those connections, boom. Okay? Simple. Really simple. Actually, the microphysics is probably devilishly difficult. But the global scale, it's astonishingly simple, right? And that's what I think makes it hard for people to grasp. Beautiful illustration on the left, slapping the data onto this. You'll notice that I've not only put the sunspots and black dots, but there's little green traces on this thing too. Those are what we call filaments or prominences, and those are the things like that erupted near the sun's poles the other day. Okay, so you'll notice on this that there's 2 excursions towards the sun's poles from those little filaments. Those are identically when the sun's magnetic field reverses. Okay, why am I interested in the polar regions? Is because every 21.8 years, it does the same thing. Okay, so schematic I developed with Frank for a lovely series of papers that some of you may have seen. And I thought I would try and go to town and illustrate all the connections. So I'm going to not talk about this. Okay. But it's basically the interaction between 2 bands on the way up, 4 bands on the way down. Solar minimum is when there's nothing. You need a termination event to make stuff happen. That's it. Now, the crazy thing that we do, solar physicists, is we love to characterize stuff by measuring it from one solar minimum to another solar minimum. Can you see how that might be a problem? Because how in that span of 6 years, if I say look from 2007 to 2012, where is the bottom of that? How do you define that? Seems to me there would be a hell of a lot of latitude in playing with that, right? Turns out, one of the fun things you can do, once you know when these Terminator events happens, you can develop pretty robust climatologies. And so I'm going to show you some of that later on about F10.7 and why we might be in fun times for some propagation coming up. So anyway, so linking these small objects in the sun to the Hale cycle, looking for the Terminator. There's an example of the Terminator in 2011. Stuff at the equator, boom, nothing at the equator. The challenge is, when's the next one going to happen? And that's where we were, right? I was also dicking around with longitude. If you remember, I talked a lot about the fact that the sun isn't actually flat. You aware of that? It's a large rotating ball. And just like other large rotating balls, there's a lot of physics that happens to be longitudinal. And that's another thing that's completely missing from a lot of our standard texts, is the longitudinal behavior of the sun. So anyway, magnetic Hale cycles overlap and interact. They have regular starts at high latitudes. They don't magically appear at 33 degrees. They magically appear at 55 degrees, and we have no bloody idea why. Okay. Migration time to the equator is variable. That's a kind of cool thing. Might not get there, but it's a very cool aspect. It's a very specialist thing that would get me hung. So anyway, and the interaction between these overlapping systems isn't always the same, which means that the output of that is not always the same. Okay. So the interaction of those things shapes the evolution of sunspots, including their amplitude. And so that's one of the things that we've pursuing for the last 5 years in particular, but really after for the last decade or more. So one of the things that, sorry, Rob.
Scott, let me be selfish for a second and ask you a question. So the timing of the timing of the Terminators, how do we know when a Terminator has happened? It's because we go into that null. Oh, okay. Well, I'll just go on, McDuff.
Yeah,
go on.
Yeah. It's measuring that null basically, and then from that null, there's a whole shit ton of other things that happen, right? And so I'll get there. Hopefully, I've got enough. But you can ask me again in 10 minutes. Okay. But yeah, so timing the terminators is actually a very important step of understanding not only when things are happening, but also to place things in a broader context. That's the kind of cool bit to me that I don't really get into in this presentation, is this idea of a clock. Renormalizing the sun's clock based on terminators is actually a really fun exercise. And it's allowing us to do things that we've never been able to do before. So it's an important thing to quantify. So I don't know if I'm pretty sure I talked about this last time, but when we went hunting for terminators in the historical data, and we used this extraordinarily weird thing called the Hilbert transform. So for those of you that are techies, maybe some familiar with Fourier transforms, but the limitation with Fourier transforms, of course, is that the phase is fixed. And for a non-stationary time series like the sunspot cycle, that's not actually a brilliant approximation. The phase is sloppy as hell. And so the next level of abstraction would be to use a Hilbert transform. So a Hilbert transform, when you apply it to a time series like the sunspot number, for example, on the top left here, gives you an amplitude function and a phase function, right? So it's the variability of the phase of all the cosines and sines as a function of time, and the amplitude of the cosines and sines that you add together to make the signal. And when you put those on a plot, you get this really cool thing at the bottom. And I'll draw your attention to two things. The phase pattern goes through zero, and the amplitude function peaks identically when one of these terminator events happens. Okay, so it's like the maximum rate of change in the number of sunspots happens once per cycle. And based on the contemporary data where we've done 4 or 5, actually we've done 12 in detail, this was pretty damn good, because one of the queries about our work was, well, that you're cherry picking again. You're forcing it to happen then. I said, well, the question was, can you do something algorithmically to prove that you're not cherry picking, right? So we developed an algorithm. It's really bloody simple. Here you go. You could do it yourself, right? Download the data, apply a Hilbert transform in your favorite tool. There you go. Bingo. So we got into an experiment. Okay, so now we're starting to smell a rat. So I'm going to ask you to visually compare the bottom plot and the top plot. Do you see the times when there's not many sunspots? We call those grand solar minima, right? So in this example, there's the Dalton minimum around 1800. Focus there for a second. What do you notice about the red stripes in the bottom plot at 1800? Are they concentrated or are they separated? They're separated. If we go to the golden era of ham radio in the 1950s and 60s, and you see that large peak, what happens to the terminators? They're compressed. So it would appear to be that the timing separation between these terminators is some kind of crude proxy for amplitude. Okay, but it's better still, it's telling you about the amplitude of the next one, not the current one. We'll prove that in a second, right? So 2 experiments. We've got 24 data examples now. In my world, that's a lot, right? Okay, 24, good number. Not as good as 42, but it's okay. So I'll be dead by the time there's 42. So we're going to compare 2 things: the peak of the sunspot cycle in between, and the next one, the upcoming one, to see if these terminators are telling you about how these hail cycles interact with one another and whether or not one cycle is actually eating the next one. Okay? So if I can look at the intermediate cycle strength, 0 predictive capability, right? So there's no relationship between the separation of these things and what's happening in the middle of them. And this is what got us really excited in 2019. Because if you compare the terminator separation to the upcoming cycle strength, you get an incredible relationship. drops right out, right? And it nails cycle 24 that nobody predicted properly, etc. I could go into town on this. But based on our best estimate at the time, cycle 25 was coming in the June or the December of 2020. And that gave us a massive cycle 25, right? Huge, potentially top 5, as my buddy says, on the podium, right? Right? Well, the one large caveat at the end of that paper, which is actually one of the most read papers in 2020, is incredible, right? The last sentence was, well, this is all well and good, but we have to wait for the Terminator to happen to finalize this, right? So anyway, so there we're going to wrap this up. I'm not really wrapping up. I'm just contemporizing myself, right? So we've seen hail cycles. The data seems to support that they interact with one another to modulate the patterns that we see in sunspots. We've used the key feature in hail cycles, their death, to establish a relationship that allows us to look at the future. That's pretty cool. And I've sold my own goat here. After much waiting, the hail cycle allows us to finalize our projection at 190 plus or minus 20. I'll justify that in a few slides. This picture of solar activity is really not what's in the textbooks. Okay, it's not. I outlined some of the caveats earlier. This is a bone of contention that's kind of rumbling along in the background in my community and probably won't be resolved for quite some time. So, but cycle 25 presented us with an opportunity that I'll discuss a little bit later, and I discussed right at the opening, the very stark contrast between what we're seeing and what everybody else thinks is going on, okay? Presents an opportunity that maybe the physics of what the sun's doing isn't as well understood as maybe they thought. So the Terminators also provide a time to explore climatology. So shameless Arnoldism. If you look at the eyeballs, this is something that nobody's really noticed. One is from the left one's from 1997 and the other one's from 2011. So we replaced the eyeballs in the cyborg with the sun. It's been sitting there forever and nobody's noticed it. So I just thought I would give it away. You're welcome. Here is the end of the hail cycle that gave rise to sunspot cycle 24. Can you see it? Approximately on December 13th, 2021. Approximately. Okay? Give or take a month. But on the time scale of a month on the sun is a blink of an eye for an object that massive. Okay? That's the thing you've got to really this is a switch. Even if it takes 5 months, that's still a switch on the sun. Okay? If I add a wee bit more context, and I now look at the lifetime of the mission that I've been working on since 2004, right? Which is still taking data at the Solar Dynamics Observatory, you'll notice a few things that are kind of crazy. Well, one, you can now beautifully see the Terminator events at the equator. You can also kind of see the growth at mid-latitudes. But what the hell's happening up about 55 degrees? Do you see that contraction up there? I'll illustrate that in a little minute. Wait, I've got a nice way of looking at that. If I can contemporize even further, right, or contextualize, and I add the other satellite that I worked on back in the day and go back to 1996, there's now 3 of them. Can you see them? He's smacking you in the face. Not a fluke. No cherry picking. Okay. So again, here's the death of cycle 24's band. You can see, if you remember, we talked a lot about at the end of 24, there's weird hemispheric stuff going on around the equator, right? It would appear to die and then it would resurge and then it would go away again. You can see it kind of represented in the density of the points there. One of the things we were very curious about, of course, is you can take scans as a function of longitude. You get to see how many bands are present at any one moment in time. If you watch the movie on the right-hand side, you'll just see cycle 25 just going bananas, right? It just erupts out of nowhere. Okay. Over almost, it's sitting there percolating away, then all of a sudden it just takes off as the stuff at the equator just goes to crap. Okay. Here's the other way, if you remember, we looked at this stuff, was as a function of longitude. And so we build these things called Hofmolar diagrams, which are a standard meteorological analysis trick. So it's basically how you analyze rings around the Earth. So it represents a ring, or the evolution on a ring is a function of time. So time goes vertically, longitude, so a ring goes left to right. Okay? So each stack is how that ring is evolving with time. So if I want to compare the equator to the activity belt latitudes, that's what you get here. And this is actually the plot that I showed the last time we talked. And there's in the fall of 2020, we got really excited because if you remember our prediction, right about the election, I mean, literally November 2nd, the sun went bananas for about a month. And we're like, yes. And then we were quickly disappointed because over the time scale of a few months, it just faded away again. And this is where we were at last time. You could even see a hint, if you look in that middle plot, of the equator dying, right? But it only spread about 80 degrees in longitude, and then it resuscitated itself, bastard, right? Let's look at the contemporary one, and I apologize that I've changed the color table, and I did that because a referee in our most recent paper complained that not cherry picking, but I was using a color table that specifically exemplified changes, right? So I was cherry picking the color table to emphasize the change. And so they pointed me at a directory of color tables for colorblind people. And so the idea is that a change is a change, and it's not some fluke of how you construct the color table. So here you go. Okay. So here's the same plots, south, equator, north. Can you see the equator dying in the middle plot? It just goes. Okay. It spreads to all longitudes in almost no time. When it actually happened, and then correspondingly on the southern and northern activity belts, guess what happens? It springs to life, right? Cool. Yeah, that is cool, actually. The other thing that you notice is there's another line on here. Now, I'm not going to talk about that other line. See the line that's in September of 2016? That's kind of like the opposite of a Terminator. I won't get in there. Maybe someday we'll have a talk about that, because this is when things die. That's your decline into solar minimum. And it's really fascinating, but I won't get into it here. But I'll show you in a minute how it manifests itself again and again and again, both of these things. So, hey, hallelujah, we can finalize our forecast for cycle 25, right? Bugger, now a year and a bit has passed. So we have a 10.76 year Terminator separation, and that's the green dot. Still sits on the line, amazingly, right? The line hasn't changed, but it sits there, and it's sitting around the historical average, which is still 2 times bigger than my peers' consensus forecast, which is the magenta thing down in the bottom left-hand corner. Okay, so there's our forecast. Let me show you some of the things that happen when you have a Terminator. Do you remember these things called the cosmic rays? And the last time we were talking about how the cosmic ray flux was the highest it had been in the space age, and how, what we expect when we see the Terminators, it drops like shit. Well, guess what happened? Why is that? Because the sun's magnetic field is like an umbrella for the solar system. And so all these things that come raining in from the outside the solar system, these particles that are supernovae remnants and things like that, and fast photons and electrons and all kinds of exotic things that come screaming into the solar system, get ducted around by the sun's magnetic field. So as the sun's magnetic field puffs itself out, the flux of these things that hits the Earth goes down. I think that exemplifies that it went down. Okay, that's a pretty huge drop. Just to emphasize how huge a drop that was, the black line is the 13th of December 2021. Anybody want to argue? You're welcome. All right. What about happens to the sunspot number at the same time? Can you see the Terminator in that data? Top plot, bottom plot is the progression with latitude. Top plot is the hemispheric sunspot number again. So this time white is total, red and blue are hemispheres. Yeah, it jumps. Okay, no, not a big surprise. Oh, sorry, my apologies. F10.7, so the 10.7 centimeter solar radial flux, which is such a beautiful indicator of complexity and activity in the atmosphere. Guess what? It jumps. Had we talked in between times, I would have shown you that what the false starts do. Right? So there was if I could flip back here, Rod, and I draw your attention to May of 2021. And I think we've seen this. Maybe we discussed it. There's a false start there. You look at the equator. Can you see it? So starts off around 40 degrees longitude and zips that way around the sun, then dies. There's another false start. But if I flip to the F10.7, there's a plateau around the same time. Do you see this? The middle of 2021, where it actually just jumps up. It jumps up by about 5 solar flux units, the baseline, and the amplitude of the wobbles gets greater. And then you see the Terminator, right? And now we're in this kind of linear growth phase. You see that between the middle of 22 and on, there's a kind of linear growth phase. If you draw your eye through the minimum of the sweeps, you can see that it's entered into a kind of different growth phase. Where we're at right now, last month was bonkers, completely bananas. Can't think of other superlatives, but there's still a lot of longitudinal things going on. So the sun has very active, so about 2/3 of the sun is now active, and 1/3 is kind of like sticking its finger up, right? It's not really getting with the program yet. If I show you a movie, your challenge is to figure out when December 13th is. Oh, there it is. Okay, so the plot on the left, I think these cover the whole year of 22. So they start in the middle of 21, go through the Terminator, and then to the end of 22. Okay, so your challenge is to, as it reverses itself, when does the sun quiet back down again, and when does it become more active? I'll let it play a wee bit. So on the left-hand side is about 150,000 Kelvin. The middle of the outer, where the inflection curve in temperature starts to turn around, and then about 1,000,000 degrees Kelvin on the right-hand side. Yeah, beautiful, isn't it? I wish it was a bit more dramatic, but whatever. So that's an image a day. And then, of course, last month, the sun was going absolutely bananas. And we got, in the space of a week, we had 4 or 5 X-class flares, which are not great for you. But, they certainly garner the interest of the journals around the world that the sun may be awake. Talking about longitude, and this is one of the things that I think is one of the greatest discoveries or the greatest applications of data science in the last 20 or 30 years, is that my colleagues that apply seismological techniques to the sun actually have the ability to sense when there's a magnetic field on the side of the sun that's facing away from us, right? So they call it far side. I've always called it backside because I'm Scottish, right? What's going on in the sun's backside today? Heart, 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 right? Canadians will get that too, I guess. But you know, what you should look at here is that so the inference patch is the yellow bit. Reality is the gray and black and white bit. And so you can see as this thing rumbles along, and again, it's longitude, right? You can see that where they seismologically detect that there's something going on with their waves, there's indeed magnetic field there, right? It's really cool. And so, you know, when I look at contextualizing the present state, this is the one from this morning, and we were talking about how there's 2/3 of the disk has got activity on it and 1/3 sticking its middle finger up as. There you go. Right. And so for the next several rotations, we're going to be seeing this kind of stuff. But that means that the F10.7 is going to get baking, which means that the ionosphere is going to get rocking. And you're going to get propagation at 6 meters and fun stuff, right? So where's the forecast at? How are we doing? Right. So we dialed in our forecast based on the 2021 Terminator. And there it is in red. The blue one's still the blue one. Seems to be doing okay. Not much to crow about at this point, because you'll notice that we've also we didn't shift the time of maximum. We've always been sitting there. But that's something I'll get to in a second. If you've read the paper, it covers that a wee bit. Here's the detailed look. Remember this plot from earlier on? How are we doing? Not bad. So anyway, talking a wee bit about maximum timing, and I'm not going to get into this in a ton of detail, but we've been tracking using polar evolution to try and help us identify when the sun's magnetic poles flip. And when the sun's magnetic poles flip is usually about the time of sunspot max, right? It's just the kind of historically observed thing. And so if I compare, so the thing I want to draw your attention to is the plot at the bottom, okay? So top, sunspot number, second plot down is the polar magnetic field as measured from the Wilcox Solar Observatory at Stanford. C is something that I've never talked to you guys about, and I'm not going to talk about it right now, but it's measuring the global topology of the sun. So looking at the morphology of the large-scale loops, right? So if you can track them, you basically get this repeating pattern, which is itself tied to the Hale cycle, okay? So that the C there is a superposed epoch analysis. So that's what we think it's going to look like if the Terminator to Terminator to Terminator cycle behaves again and again and again. The thing on the bottom is the real data, okay? There's an extension in the real data. I'll flip back and forth. You'll see that the thing's rising up towards the pole, which means that the polar magnetic fields are closing, which means that the polar reversal is happening, which means that solar maximum is within 9 to 12 months from now. Okay? That's basically what it means. I can do this from endless numbers of spacecraft. Same thing. Cherry picking again, right? Love to cherry pick. I can look at it in different measures, right? So this is now looking at 3 different spacecraft, looking to see how those polar coronal holes close. If you look at the very end of the time string here in 2023, January, goes up to last week, you'll see that these black things have come into an apex, which means that the polar coronal holes are closing or have closed or at ridiculously high latitudes. Why would I be interested in those polar vortices of the last couple of weeks? Is that to do with the polar reversal process? Something we did with Frank motivated this, was to go back and look at F10.7 over, when did we start measuring that? 1947, I believe the record goes back to. And what we did is we sliced the data up, Terminator by Terminator by Terminator, to try and construct a climatology for F10.7. So we normalized it And then what we did is we kind of re-stretched time. So we think the next Terminator at least is going to be around 2032. Okay. You get into the sophisticated math of why, because it's 10.86 years later. It's a sophisticated math. We can't change that until we see cycle 26. When we say cycle 26, we'll be able to figure out where that right-hand side is, right? But best guess is 10.86 years later. That's the average. 2032 and a bit, okay, would be the next one. So we construct that. We have a good idea of how sunspot cycle amplitude and F10.7 correlate. So we set the scale. So here's what we have, okay? This is, I think, from January. So blue data is the monthly averages. Red data is the daily data, smoothed. I think it's smoothed over a rotation. Okay, started the window. Oh, there you go. Okay, that's last month. Look at that thing going bananas, right? You notice that I didn't put the NOAA forecast on here because I think it's unfair. Right? It just looks awful. So I didn't do it. Because there is a nice part of me, believe it or not, right? One of the things that I've learned in this interaction, especially with hams, is that the ionosphere isn't really other than blackouts. It takes time to bake it, right? To get it up to the point where propagation becomes booming. And so it's really the brown curve there, which is the kind of 81-day average F10.7, and the average kind of sunspot number. Once they get up to like into the 170s and 180s, you get propagation down at 6 meters and things start to get a lot more fun, right? So just been watching these indices grow. They're growing by about a point a day at this point, which is kind of cool. Which means that you're going to be in that sweet spot around the March and spring equinox. It's going to be awesome for those in the northern hemisphere, kind of sucks for everyone else. But anyway, but you'll be able to place lots of games. So, as if by magic, here I'm at, right? We came from 2002 into 2012 to 2020 to 2021, and now we're in 2023. Things happened, right? What we're waiting on now is to see. I've moved on. I'm waiting for 26, right? So I'm going to be watching for 26 appearing about a year from now. Okay, I should be able to track it in things like this. Okay. Because you see the overlapping patterns in this thing. There's 4 or 5 different diagnostics. So right about solar maximum, I should be able to start picking up cycle 26 at high latitudes. Then I'll start adjusting the Terminator, and I'll forget about 25 and start worrying about 26, right? So there's the kind of forecast. If any of this pans out, we need to really rethink about what we know about the inside of our star. Okay, that's the kind of, for me as a physicist, this is what it means to me, right? Is trying to explain and understand through the photons that we catch, right, how this damn thing works, right? The better we can understand how it works, the better we can forecast how it's going to behave. All right. So if we're sending astronauts to Mars and things like that, I want to be able to nail this shit down. Right? No shit. That also includes the flares and CME stuff that I don't talk about. That's completely related to those bumps and wiggles. Those bumps and wiggles are called Rossby waves, right? And so there's the same things on the sun as there are in the Earth. Right, and the global scale weather of the Earth is controlled by these large scale global scale waves, right? And understanding those global scale waves allows you to better predict what weather is going to look like, a few days in advance. There's no reason why you can't do the same thing for the sun with these diagnostics that I presented to you. Okay. Now, if you've got a couple of minutes, I'm going to go into this a wee bit more, okay? So this just smacked me in the face. It looks like a lasso. If I make you a movie where you see, and I should have put it in here. I was kind of not caffeinated, I guess. If I make you a movie where it's a running difference, and I posted this on my Twitter feed, you can clearly see that this thing sheds. It's like a ring, and there's a wave that goes around it, right? In the space of 24 hours. Things moving at about 100 kilometers a second, okay? And in solar context, that's not super fast. That's pretty damn fast. 100 kilometers a second is pretty quick, okay? Remember how I said earlier when I was looking at the Terminator and what happened? I am now starting to really dial into what's going on at high latitudes because, again, I'm looking for cycle 26, right? So I'm refining a lot of stuff now to focus on that band at around 55 degrees, right? And here's some of those Hofmüller diagrams now for that region between 45 and 60 degrees. What happens at the all right, the pre-Terminator, the decline to minimum. We've struggled with names for that. But given, here's a jokey thing. What came before the Terminator? Was it James Cameron? Was it Michael Biehn? Was it Kyle? Was that his name? So we've been trying to figure out what the hell to call these things. So if the Terminator is the Terminator, what comes before the Terminator? So we start with Cameron, right? And so you see the September 26 Cameron and September 2016 Cameron. What does it do? Do you see the stark difference inside of those regions? Things just so you see this blossoming of stuff at high latitudes, which switches off again at the Terminator. It was some weird shit, right? We've no idea what it is. But it happens again and 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 again. Why? Because the thing's cyclic, right? And so this is a plot I've been bludgeoning people with for about 3 years. And I apologize. Well, I actually really don't. I only a little bit apologize for the complexity and the octal diabetes, right? If you look at the top left-hand side, you'll see what we call the polar crown filament in all its glory. Look at that thing. It looks like reindeer tripping across the sun, right? Well, it's not. It's marking this line where the sun's magnetic polarity is changing, right? That's basically what it's telling you. It's telling you the interface between the different polarities. The thing in the top at the middle is the progression of these things as a function of time. Remember I said they go to the poles once per time, and it's triggered by the Terminator. And then we see the stuff about polar coronal holes, and then we see the stuff that's happening inside the sun. We call it the torsional oscillation. It's probably not. It's the fact that there's a very strong magnetic field there. And then there's the fact that weird seismological stuff happens at 55 degrees. Why the hell are we not flying to the sun's poles to measure this shit? Serious question. Right? If you're scholars of one of my, I guess, in principle, distant relatives was a guy called David Livingston, who, along with an American called Stanley, went in search of the source of the Nile, right?
Yep.
Based on a hunch. Why are we not going looking for the source of the sunspot cycle? Just to illustrate how cyclic this thing is, I don't know if I showed this in my first presentation to you guys. This is what we call a superposed epoch analysis, right? So you take a chunk of data, you move your window by 11 years, and you take another chunk of data, and then you statistically stack them all up. And if it's really cyclic, the average should be very clean. You see the average. This is the filament record going back to 1860, so this is 14 cycles. Right? And you'll see how sparse the data is at the start, but it gets really much cleaner as we go through time. Look at the average. Boom. Remember, this thing, where you see filaments on the sun is where the magnetic fields are canceling. Look how complex the picture gets when it gets to the average. Boom. But what do sunspots do when you apply this trick? You see any overlap? Let's see. No. But amazingly, they all stack up beautifully around the Terminators. If I did this trick with solar minimum, it wouldn't be quite as pretty. So just to compare all these things, do you see a similarity in all the patterns? I'm cherry picking, clearly, right? So using 150 years of data to do it. I haven't even shown some of the things in here. But sunspot cycles are just a subset of this larger scale behavior, right? And so it seems like these Terminator events are really critical, but only critical in the sense that they tell you that the bands on the inside of the sun are playing with one another, right? So, and with that, I'm spent.
Well, we've asked you to talk quite a bit, and I got to give you credit, Scott. One of the reasons I love your talks is there's a lot of humor. I think sometimes it's a little too subtle, even for us. In the cherry picking comments, I know, because we know the history, so a lot of the folks get this.
It just pisses me off, Rod. That's why.
Yeah, no, and I know, and I thought you showed considerable constraint this time around. So, good for you.
Thank you.
Those grants will start coming now.
No, they won't. No, they won't.
Well,
because anyone that is vested in us being wrong is on the panels and make sure we don't get funded.
Yeah, but there is patterns are really, really powerful things, right? In not just this, but in life, right?
Correct.
And
yes.
So to get people thinking in a different way, you've got to provide compelling, and I would argue visual evidence. And I think Frank would go with me on that one, is that to get into people's dinosaur brains and get them to truly think about stuff, for humans, the compelling thing is visual patterns. And this just happens to be a media where I love what you've done with it. What are the... Maybe I'll get you fired up here. Do we have enough data collection on the sun right now? Like if we let that slip in terms of the various satellites and, as you say, visibility to the poles, that kind of thing, and how do we change that?
All right, so there's a kind of interesting revolution going on in science right now, generally around AI. Right. And AI is not new because I wrote my PhD thesis on AI 25 years ago, right? Neural nets and things like that. It's just been kind of recast, right? Bigger computers, more expensive computers, and it's just been kind of recast. But it's the same methodologies. It's correlation and understanding how systems work together. If you listen to the AI proponents, we don't need to do anything anymore because AI can do it all, right? We don't even need to observe. Right. I roll my eyes at that as well. Right. Yeah. As a director of one of the world's oldest solar terrestrial physics labs, I really struggled with this idea that there's two types of observation. There's synoptic scale observation, which is the sun is a star, large field of view to study global scale phenomena. Right, mm-hmm. where the course of study takes a long time, right? A decade. A sunspot cycle is a decade, right? But on the other hand, there's these phenomena that take place in seconds and minutes and a few hours that happen in very high resolution fields, and so there's this constant battle in my community between the balance between global scale and very high resolution. And the problem with, and I'll say this, everybody thought that the cycle stuff was all dialed in. And so for about 20 or 30 years, they started closing down a lot of the synoptic scale observatories. So some of the data examples I showed you end in like the late 90s because budgets, right?
Mm-hmm.
And they were trying to focus more on the high resolution stuff, because the big scale stuff is all solved. Solved. Right? That the emphasis then became on understanding the minutiae. And the problem is that the global scale stuff is really not solved. Right? And so, but once a historical data record is gone, it's gone. And so one of my jobs was to try and start to reconstitute some of these historical measurements, maybe with new instruments, but also to provide the kind of analytic framework for them to be practical, if that makes sense, right? So like the thing about the coronal morphology has been done for 40 years, and then they switched the telescope off in 1996.
Yeah. And having worked within AI teams, actually developing applications in that area, the thing that you'll hear from the model experts is we don't have enough data. We don't have enough data. This is why the model doesn't work, because we don't have enough data. And it's like, guys, to me, okay, that might be a valid point. It probably is. Maybe your model sucks. But like, not your model, but I mean, maybe whatever AI thing I'm working on. But if I don't have enough
that
data,
phrase, right? Crap in, crap out.
Right.
If you're putting crap into it, you're going to get crap out of it.
So, it's been my look at this where, as I've seen commentary on this talk of, oh, well, this data, I've heard this before where this data ends at this location. And it's like, guys, when we're dealing with decades at a time, you can't afford to switch it off. You can afford to maintain it at a minimum, maybe. Just collect what you did before. Maybe you don't collect new stuff. That would suck, but it doesn't suck as badly as actually turning it off. So, yeah. Oh, by the way,
one of the things that's important there in this context was nobody had ever stitched it all together, right? So they're switching all these things off. And it had never been, like I hinted at work that was done in the mid-80s, right? They were so close, right? It's astonishingly close.
Mm-hmm.
And then the work just deep sixes, right? It just disappears, right? 86 is the dawn of large-scale available computing.
Yeah.
Right? In the mid-80s. And so these observations don't stack up against the sunspot models anymore, or the global scale dynamo models anymore, right? And so it's a crying shame. And I always try to recognize the pioneers in that area. There's only a couple of them left now. And so I've worked very hard with them over the last few years just to interview them and talk to them and find out what they did and what they knew and where they were going with their analysis. But this is the problem, is that whole work just gets mothballed, right? And that's what's hard for me, is I wouldn't say I'm a Renaissance man, but I do admire the insight of the observers that came before us, because they didn't have SDO where it's taken petabytes of data a week, right? They had 2 or 3 images a day to work from of high quality, and they studied them in great detail, and they produced all these beautiful diagnostics. Mm-hmm. And we just kind of flush it down the toilet. So that's hard for me, because I there's so much value in it, because I've been doing all this forensic analysis, right? The kind of archaeosolar physics, if you like, right? So there's real value to it, and now it's a case of how do you restart it all,
right?
So sorry, I didn't mean to interrupt you, but
no, that's I couldn't agree more. Hey, we've got Lisa Peddington. Now, Lisa, I apologize for butchering your surname there, but I put a couple of questions. One was a comment she put in. You're asking about what do we call it before the Terminator? And she said the Predator. So I wonder if
I'm
that's
not sure with contemporary use of the word predator. I don't know if that's a good one.
Yeah, exactly. I think, but I appreciate the effort.
Get it.
Well,
get
well
it.
done, Lisa. Well done.
We were thinking more of Kyle Reese, because Kyle Reese gave rise to John Connor, who gave
exactly,
rise,
exactly. Yeah, now you have to be a Terminator nerd, but aren't we all? So,
nerd.
Lisa was asking for the magnetic feature. I just put it in the chat here. For the magnetic feature, is that an up and down movement, or internally gyrating? I'm thinking 3D, I guess. I think she's referring to some of the magnetic flipping model. And Lisa, there's a recording on this YouTube site that took you through some of this terminology from, as we said, about 16 months ago. So have a look at Scott's first presentation there, where he goes into quite a bit about, how the sun does flip over. But I appreciate the question. That's awesome. Any questions from the team? Just unmute.
Yeah, and thanks for sitting through that. I didn't realize it was going to talk for so long.
That's really good.
Frank will go, yeah, you just talk like that long all the time.
Scott, great discussion. I always continue to learn whenever I see your updated slides and things like that. I go back to writing some simple rule-based prologue of what was called AI then, and one of the issues I see, and a lot of this comes from Judah Pearlman. Judah Pearl, if you remember Daniel Pearl, the Wall Street Journal journalist who was murdered, his father was a CS and philosophy professor at, I think it's UCLA. He's retired now, but still writes about causality. And the problem with current AI is if you learn rules, that is, you're not doing the rules by querying experts, you're using data to generate rules. And that's kind of what that's what the chat GPT, all that's based upon data generated rules. Well, if the data have a heuristic limitation, then inherently you're going to get, learning, if you will, that's based upon that. And I would submit a paradigmatic jump will go to a different heuristic. And that's what you're doing. And that's one of the reasons why the standard grant proposal writing, having been both at the seat and at the head of the table, keeping the cats from fighting over the cat food, they will get these McIntosh people out, and they're worse than 2 9-year-old Philadelphia Phillies fans that give you the double bird when you come out of the tunnel, as Peyton Manning said. That's the way they tend to act, and the head of that panel has to keep that. Here's the difference, I would say. I always embarrass Scott. If he got ran over by a dump truck today, heaven forbid, or if his children decided they had enough of this.
We're leaving Colorado. Yes.
Yeah.
Well, it wouldn't die with Scott because he's published too much stuff. That footprint is there. I'll add this, Scott, as a ham, and I often wave. I'm not a solar physicist, but I know a really good one. And listening to him, we need to do at least a couple of things. We need to take sine wave and put it on the side and pick up whatever the current metaphor is. A paper that Scott wrote with Bob Lehman. It has a solar clock. We need to change the metaphor of sine wave because that's the outcome of all this stuff Scott's studying. That's the realization. What's causing it? All of our books don't talk about that. They take it as given. So that's one, we need to change how we look at it so we can better understand what Scott's talking about. And Scott, I'll really show my ignorance now, but Peter Wilson in your citation was a bathymetrist. He studied flux tubes, but they were water tubes under the ocean. And my friends who chase submarines, or a submarine can do a lot of things, They can run silent. They can run deep. We got movies about that. They can't replace their mass. They can't. And so
Right.
if they screw up the standing waves under the ocean, just like the Predator movie, you could see them if you had a different sensor. We can sense that. So what I wonder about when you get the false start, and I wonder about the Bernoulli principle, and this may show my terrible ignorance. It was based upon stuff that may not apply to the sun, but it was based upon pressure and speed. And so you've got this 127-day cycle where boom, and I think Dick Potty's simulation that you shared kind of shows what happens with that. I don't know if any of those kinds of thoughts are relevant at all, but I'll kind of end with that ignorance that I've now shown the world.
It's not ignorant. I mean, this is the thing, right? It's, I took the time a couple of weeks ago to sit, and I've never actually committed all those thoughts to paper, right? That, and so for the first time, because one of the things that now the emphasis on a theoretical framework, right? So that's where we get hammered now, right? It's the data is as clear as the data can be, right? But now it's you need the theory now. Well, before it was the non-cherry picking algorithmic approach to identifying them, right? Now it's you need the theory to explain it, and so this is where I think a lot about pressure balance, and familiarity with where Peter Wilson was going, right? And how his particular area of expertise allowed him to think about the processes. And there's so many things where buoyancy it's a pressure phenomena. And so that here's the challenge though, right? Where the sun is a plasma, you actually have two components of pressure. Not just the pressure term in the fluid, right? The magnetic field has its own pressure. And so what you're really looking at is the balance between the kind of background pressure and the pressure in the field. And so those vortices are the same, right? They have their own intrinsic pressure induced by the rotation, and it's kind of fascinating, the similarity in the physics. Right, that it's not. I mean, the minute you mention Maxwell's equations, people's head explode. Right, when I talk to meteorology students, and I'm trying to convert them to come and work in our field because they're better equipped than astronomers and astrophysicists, in my view. Right, especially with the way we're going with data immersion and AI and all these kind of things. That taking the kind of more meteorological approach to our stars, the way we're going to advance understanding. And so you need to kind of put this old astronomical single slice in latitude, no longitude picture away. You can't disconnect them, right? They're all intrinsically coupled. And so, this idea of global scale pressure, it is something, and in fact, we've been hammered a number of times for using a term. We call it magnetic teleconnection, right? You've heard me use that term before. And that's what teleconnections, what is happening inside of planetary atmospheres, right? It's how the global scale waves in one hemisphere talk to the ones in the other hemisphere, right? They do talk. They use internal gravity waves and things like that. So the information is carried. And so this world is now about trying to understand what the medium of communication is, right? It's how is information, why are they so synchronized? What's doing it? How the hell is information carried from the equator to 30 degrees latitude and then carried to 55 degrees latitude in that time? That tells you about what's going on in the ocean. Right, it's like it's the thermocline, right? You're probing the characteristics of the thermocline, right? If I use, and so it being bilateral, it is kind of scientifically bilateral or scientifically multilateral is really important, because it's like I see the limitations in the the astrophysical approach to the our star, and I can guarantee that our star is not special, right? So if I go to the astrophysical approach, the minute we start to unlock this for our star, other stars away, right? And depending on how fast they rotate and all this other stuff, will set up different kinds of patterns. And so you can actually test the model ad absurdum there. The one problem we have is Maxwell's laws, right?
So-
because if you look at a point object in the sky and you put your big magnetogram filter on your telescope, Maxwell's first law kills you, right? The divergence of B is 0. Magnetic fields cancel, right?
Mm.
So you then have to look for sun-like stars that are pole-on, right? So you only see one pole. So you actually try to measure the Hale cycle on those stars, and then try to correlate that to everything else that you see. So, I could see a rich career for myself going and exploring that crap. But they don't put polarimeters on big telescopes like Webb and Hubble to measure magnetic fields because of Maxwell's equations, right? So it's really bizarre that the astronomers are not more into magnetic fields, because there's a famous old colleague of mine said it's all about magnetic fields.
Good point.
So anyway,
So
sorry, rambling.
No, absolutely wonderful stuff. I mean, multiple literacies is a great place to end this. What we're going to do is we're going to stop the recording, and then we'll continue on just a little bit. So for our friends at YouTube, thank you so much for showing up. Scott, where should people find more of your stuff? Why don't we plug that?
We try to confine a lot of stuff to Twitter if they want to follow there. At SW McIntosh, you can find me there. Mostly just talk about solar activity and stuff like that there. So you've seen the feed. Most of it's complete drivel. So there you go.
But it's good fun.
Sometimes I'll get agitated, and then I kind of have to hold myself back. So.
Well, you've been very
obvious.
controlled today, Scott, and I really appreciate your time. So let's go into the After Dark section. Thank you so much, YouTube. I'll see you guys